Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting model called as Rho1, which is basically based on this philosophy that not all tokens are what you need for pre-training. This was a NeurIPS 2024 Best Paper Run-Up. It won the NeurIPS 2024 Best Paper Run-Up Award. So let's get started and understand, what is this philosophy of not all tokens are what you need for pre-training, right? So in fact, this strategy is also called as selective language modeling. So let's understand why is language modeling needed and what benefits one can get from that, and therefore, come up with this model called Rho1. Okay. So, standard language model pre-training involves next token prediction loss, and that loss is computed for all the training tokens, right? In the pre-training corpus, you have a pre-training corpus, and you essentially try to do autoregressive pre-training by computing this next word prediction loss for all training tokens. However, there is this interesting, curious question, that are all tokens in a corpus equally important for the language model training, or some of them may be noisy, some of them may be tokens that are insensitive to the kind of task that you want to do, and so on. And therefore, you may not really need them for pre-training. Okay. So therefore, what these guys did was to essentially, experiment with the pre-training corpus. So they actually tried to pre-train small models like Tiny Llama 1.1 billion and Mistral 7 billion, right? So and what they did was to pre-train using a 15 billion token corpus. Okay. They also held out a separate validation corpus. So remember, whatever charts are not drawn for pre-training corpus or loss on pre-training corpus, but the loss is computed on a separate validation set. Okay. And on this validation set, they tried to figure out for every token, how does the loss vary as you pre-train more and more on those 15 billion pre-training tokens. Okay. So they basically computed the loss for each validation token after every 1 billion of pre-training, after every 1 billion tokens of pre-training. Right? And then what they observed is that, hey, if I take this token, at the 0th time point, and then after 1 billion, after 2 billion, after 3 billion, does the loss increase for this token? Does it decrease for this token? And so on. Okay. That is how they basically split this set of a few hundreds of thousands of validation set tokens into high to high tokens, low to high tokens, high to low tokens, and low to low tokens. What does that mean? Well, that basically means, so y-axis is loss. So what that means is that low to low tokens basically their loss starts from a very low value in the beginning and remains low forever. Right? High to high tokens are the ones where the loss starts with a very high value and remains high until the very end, until 15 billion tokens have been seen by the model. So interestingly, what you sort of, or rather, what you expect is that, initially the loss is high and then it drops for majority of the tokens, right? That's what good pre-training could mean, right? However, interestingly, it is also observed that some tokens, as depicted by this red line, essentially start from a low loss, but then end up with a high loss at the end, right? The distributions are really, really exciting and interesting. So 51% of the tokens really do not even participate in the game. I mean, it's more like, their loss was low and this just remains low in the entire pre-training. Similarly, for 11% of the tokens, the loss was high and remains high forever, right? There are these interesting, high to low 26% of the tokens that really are very, very interesting and should be really looked into while doing pre-training, right? Because that is what is sort of making the model learn things. In fact, now, of course, these are the broad trends in the picture A, right? But if you look at the picture B, that's basically focused on three selected tokens, right? And particularly those where the loss remains low to low in a broad trend. I mean, if you really looked at the zeroth, checkpoint and the checkpoint after the 15 billion tokens have been observed, right? And what you observe is that, well, the loss actually fluctuates a lot. So it's not like the loss continuously decreases or continuously increases and so on for every token. Well, for some tokens, it sort of fluctuates too much. Okay. Basically just saying that maybe these tokens are too noisy. The model is itself confused whether it should try to minimize the loss for these tokens or not. Right? And the same thing holds even for high to high tokens. It's not like the loss remains high always. Sometimes the loss becomes very low and then it basically becomes high again and so on. Net, there is distinct loss patterns for different tokens. And therefore, they came up with this technology, this methodology, right, where they try to do selective language modeling. They still do causal language modeling. It's still mixed token prediction in some ways, but the loss being computed only on a few tokens. Okay, so the philosophy is actually nicely described in the picture at the bottom. So you see there is a noisy pre-training corpus. And just to show a good example, they basically said, well, the original text could have been just the farm has 35 hens and 12 pigs, but there were noisy tokens here, right? And while in causal language modeling, you would compute the loss on all the tokens, whether they are noisy or not, right? The blue and the red tokens. In selective language modeling, you would not compute loss on these noisy tokens, X2, X4, and X5 in that senses. Okay. But then the point is, how do you find these noisy tokens, right? And that is why they have come up with this interesting methodology. The methodology works in 3 steps, as is shown in this picture in the middle on the right side, right? So essentially, you start with a very high quality corpus, and of course, you start with some small, with some language model. So they experiment with 2 different language models: Tiny Llama 1.1 billion and Mistral 7 billion. So basically 1 billion and 7 billion kind of models. Okay. So you train a reference model on high quality text. So basically the idea is that you first select some high quality text and then you train a language model. So you assume that it does not really have any noisy tokens. You want to train it in the simple causal language modeling manner, autoregressive language modeling without any selection and so on. Okay. So you train this reference model. So actually they train these two kinds of reference models: math reference model and general reference model, as you see on the left side, right? The math reference model is trained on 0.5 billion high quality math related tokens, and the general reference model is trained on 1.9 billion tokens from open source data sets, high quality once again. Okay. So the reference model is very clean, is trained on very clean, nice, high quality data. Okay. Once you get the reference model, you take the pre-training data set. Now remember, this pre-training data set is different from the high quality corpus. The pre-training data set is the one that you actually want to use for real training of your model. Okay, and it's much larger in that senses. Okay, so you basically take your pre-training data set and compute each token's perplexity in the pre-training corpus using the reference model. Okay, so you're assuming that your reference model has been trained nicely, on high quality data. You calculate each token's perplexity in the pre-training corpus using this reference model. That's step 2. And then you get basically a pre-training corpus where for every token, what you have is essentially, for every label, what you have is the loss from the reference model and the loss, from the training model itself, from the pre-training model. Okay, so essentially, you have the reference model loss. You basically took the pre-training corpus. You essentially computed, the loss, the perplexity for each token. So then what you do is to actually train your step 3. You basically actually train your large language model in a selective language modeling way. And how do you do this selection? Well, you basically train on tokens that exhibit a high excess loss between the reference model and the training model. Okay. So essentially, while you're doing while you're doing language modeling, you basically have their reference loss values anyway in the pre-training corpus. And when you are doing pre-training, of course, you pass those tokens through the large language model that you're using for training anyway. But then you compute loss only on those tokens that exhibit high excess loss between the reference and the training model. Okay. Now, what does high mean? Well, they basically choose high based on the top K%. So token selection ratio is fixed to top K%. So, for example, you could basically just take like top 20% of the tokens and you can train your model. Okay. Now, note that the architecture for the reference model and the architecture for the large language model that you're finally training using selective language modeling is the same. So basically, they just train 2 different models, Tiny Llama 1.1 billion and Mistral 7 billion using continued pre-training. So basically, the continued pre-training can be done using causal language modeling or selective language modeling, right? So those are the 2 options. And, so a little more details, the pre-training corpus, they trained math model and general models. So for math model, they basically used 14 billion tokens from Open Web Math. So, and this basically can contain noise and so on. So that's why they do selection language modeling on top of this. The general model is trained using a combination of Slim Pajama, star-coded data, and Open Web Math containing 80 billion tokens, right? So that's the 2 kind of math and general models that they pre-train, and also of course they pre-train the 1.1 billion and 7 billion parameter models. Okay. So the continued pre-training results are as follows, right? The right side, top chart actually shows you very interesting results. So there is a result for 1 billion parameter models that are trained, and on the extreme right side, 7 billion parameter models, right? So what do the results show? On the x-axis, basically you have pre-training being done. So that's basically 0 to 15 billion tokens. Of course, this is on math. So therefore, on open web math data set, right? On the y-axis, you basically see accuracy. So higher the better in that sense, right? What are the three curves? The three curves basically show you, I mean, this flat curve is basically DeepSeek Math 1 billion and DeepSeek Math 7 billion accordingly based on the two charts, right? And you see, I mean, the lower curve basically is the baseline curve, basically meaning if you do continued pre-training with this open web math data set on top of, tiny llama 1.1 billion parameter model, how does the math accuracy vary with 15 billion tokens of pre-training? Okay. While the red curve is the one which is obtained using selective language modeling, right? So clearly what you observe is, you observe that with selective language modeling, after 15 billion parameters, the model is able to beat the DeepSeek Math 1 billion parameter model. And the same trend holds on the right side as well. In fact, if you compare with the baseline pre-training, which is based on selective language modeling, what do you observe? You observe that the 1 billion parameter model is 16.3% better, or it can achieve the same level of accuracy as the causal language trained model 10x times faster, right? Whichever way you want to really look at the chart, right? On the right side also, you see the same kind of trends, around 16.4% better, or basically you can train the 7 billion parameter model 5 times faster. Okay, now who would not want either of the two? Either of the two is really important, and actually, right, it leads to more efficient pre-training or more effective pre-training. Okay. So net, the results are as follows. Continual pre-training basically on 15 billion open web math corpus essentially shows a gain of up to 30% in 9 different math tasks. So more details are of course in the paper, but the interesting part is selective language modeling sort of improves the average few-shot accuracy on these popular data sets like GSM, 8K, and math by over 16%, achieving baseline performance 5 to 10x times faster. Okay, so that's that. That's pretty strong a result in that sense, right? Tiny Llama 1 billion parameter model on 80 billion general tokens gives you so that was about math, right? The above one was about math. This one is about general pre-training. So Tiny Llama 1 billion on 80 billion general tokens gives you 6.8% average gain across 15 different diverse tasks. The figure here on the right bottom actually shows you those 15 different tasks and actually shows you the gains that the Rowan model with selective language modeling gives you over Tiny Llama and Tiny Llama continuous pre-trained model. So the CT model basically is, of course, trained using causal language modeling. So what you observe is that across many data sets, and again, these are like very popular benchmarks, MMLU, BBH, math, and so on, you see significant gains, on average 6.8% gains across 15 different tasks. Also, if you think about did this model achieve a state of the art? Yes, row 1 billion and 7 billion achieve a state of the art result of 40.6% and 51.8% on the math data set after fine tuning. And this one clearly matches DeepSeek Math with only 3% of the pre-training tokens. So basically, they've been pre-trained using 15 billion tokens. Yeah, I mean, it's basically 15 billion, not 14 billion, but everywhere, right? Versus 500 billion tokens, which DeepSeek Math guys used. Okay. So in summary, we talked about selective language modeling and Rowan models, which have been trained or pre-trained using selective language modeling in that senses. The basic idea is that not all tokens are equal during pre-training, and therefore selective language modeling sort of selects suitable tokens for the current pre-training stage. And that is how they basically pre-train two models, the Tiny Llama 1.1 billion parameter model and yet another 7 billion parameter model. And they show significant gains across both math benchmarks as well as general NLP benchmarks. The selective language modeling enhances token efficiency at train time and also improves performance on downstream tasks. Here is basically an example just to show, the blue kind of tokens are the ones that are selected in the pre-training corpus to be used for computation of the loss, while the black kind of tokens are not selected for loss computation. Okay, so that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage.